The kinetic theory of gases is a simple classical model of the behavior of gases. It treats a gas as composed of atoms or molecules in random motion. The application of kinetic theory to ideal gases makes the following assumptions. First, the number of particles is very large. This assumption is sometimes referred to as the thermodynamic limit. Second, the gas consists of very small particles, so that the volume of the particles is negligible compared to the volume of the container. This is equivalent to stating that the average distance separating the particles is much larger compared to their size. Third, the interactions among molecules are negligible. As a result, all the particles move in constant velocity between collisions. Fourth, when the particles collide with the walls of the container, the velocity component perpendicular to the wall is inversed, while the velocity components parallel to the wall is preserved. So, these collisions are perfectly elastic. Fifth, the time during a collision between a particle and the wall is negligible when compared to the time between successive collisions. Suppose the container is a cube with edge length L. Consider a particle traveling at velocity Vx along the x direction. The particle encounters a wall after period tau equals 2L divided by Vx. The momentum change of the particle at collision can then be described as delta px equals 2mvx. We combine the above with Newton's second law, which states that the force experienced by a particle is related to the time rate of change of its momentum, such that F equals delta px divided by tau equals mvx squared divided by L. The pressure exerted by the collisions of n particles with the wall can then be found by adding the force contribution of every particle and dividing by the surface area. Because the orientation is random, the average particle speed in every direction is identical. Combining the Pythagorean theorem such that Vx squared equals 1/3 v squared. Therefore, the pressure is in the following form. We may combine it with the ideal gas law to convert PV to nRT. The root mean square speed is proportional to the square root of temperature. This is an important, non-trivial result of the kinetic theory because it relates temperature, a macroscopic property, to the speed of the particles, which is a microscopic property. Meanwhile, the total translational kinetic energy of the gas is defined as the translational kinetic energy of all particles. Therefore, PV is equal to 2/3 of translational kinetic energy. We may also combine it with the ideal gas law to find that the total translational kinetic energy is 3/2 nRT. So, temperature reflects the energy of the particles making up the substance. For example, the root mean square speed of nitrogen at room temperature is about 545 meters per second. The total translational kinetic energy is 3.72 kilojoule per mole, which is equivalent to 38.5 micro eV per particle. The root mean square speed is directly related to the speed of sound in the gas. The speed of sound in the nitrogen at room temperature is about 372 meters per second. Here, gamma is the adiabatic constant. For nitrogen, gamma is 7/5. Maxwell-Boltzmann distribution is used for describing particle speeds in ideal gases. The distribution function depends on the ratio of the mass of the particles to temperature. At a given temperature, the distribution function becomes taller and sharper with the mass of particles. With a given mass of particles, the distribution function becomes shorter and wider with temperature. The mean translational kinetic energy can be calculated with Maxwell-Boltzmann distribution. The result is the same as the kinetic theory of gas. The mean speed of the particles can also be calculated, which is different from the root mean square speed.